We have now computed the position of the robot by adding up small motions of the robot, but why not actually looking at the positions of the wheel itself? Why this doesn't work for differential wheel robots, we will explain in this video. To illustrate this, I have re-enabled the position controller. You remember we set the position of the wheels to be infinite so that we can control them with velocity control. This time I don't do this and disable these two lines. And then I have created an array or list in Python in which we can add poses that the robot should servo to. And what I've done for that is I've set the time step to 1500 milliseconds. That means every time the loop iterates, the Webots simulator will simulate 1500 milliseconds at once. And I have a index time, which I set to 0, which gets incremented here, which will allow me to go through a list of poses that the robot should servo to. So this will servo the robot to pose 0, where it starts, and then move it to half a wheel rotation, which looks like this. Now it has moved. For half a wheel rotation, let's remove the 0 here, we don't need that. And let's move right away to rotate a full wheel rotation so you see what's going on, and then move back to 0, 0. So as you can see, the robot in this case will move forward and then will move backward now that the wheels are at position 0 again. Now, does this always work? Is it sufficient to know where the wheels are? For a robotic arm, this is the case. When you set an arm to move to certain joint angles, you know exactly which position you are at. I will show you now that this is not the case when you use a differential wheel robot. And for that, I prepared a trajectory that looks like so. We now have a trajectory in what we call joint space. The robot has two joints. Rotational joints in this case, and we have the left wheel and we have the right wheel. And at the beginning, both wheels are starting at 0, and then they both rotate forward up to 2 pi. And now what I want to do is I want to stop rotating the left wheel, but I keep it at 3 pi, but just rotate the right wheel so the robot doesn't make a left turn. And then I wind the left wheel backwards until I arrive at 0 with it, and then I rewind the right wheel to be at 0 as well. So I have prepared this in Webots, and for that I reinsert what I prepared, and you're welcome to compare these numbers. I start at pi, then 2 pi, 3 pi, but then as this moves forward to 5 pi, the other wheel stops at 3 times pi, and then it winds back to 0, 0, 0. All right, let's run this and let's see what happens. And now you can already think about whether you think this will let the robot return to 0, 0 or not. And here's the result. I move forward, then I make my turn. I do a little more turns, and then I unwind the other wheel, and I end up in this position. Now, this is not the origin, and if we have trajectories in joint space that are full circles that do not become full circles in Cartesian space, we say that the platform is non-holonomic. A holonomic platform instead would be a manipulating arm where you have 3, 5 or 10 joints. It doesn't matter, because you will always end up at the same orientation and position when you set the motors to have the same joint angles. This is why, in order to estimate the pose of the robot, we have to add up every motion that it does and see what the result is, instead of just looking at the final orientation of the wheels.